Hello, I'm going to introduce our work on unlimited learning for model update aggregation in federated learning for click-through rate prediction. My name is Shanghang Liu, and we are from Huawei Research. So CTR prediction is actually one of the most important problems in ad delivery, given features of an ad impression, including user features, ad features, and context features. We would like to predict the likelihood of click. Most of the CTR models have components like embeddings, explicit interaction layers, and fully connected layers. Some of the models also have bias layers for calibration purposes. And one of the typical example is deep cross network. So in this work, we are mainly concerned with federated learning of these CTR models. Federated learning is different to centralized training because it doesn't have a centralized data storage, and each client store the data on its own device. The learning process consists of several communication rounds between the server and the client. At communication round T, the server will first send the model weight WT to each client, which performs a local update over its own dataset DK. And after we collect all the updates from all the selected clients, put them into a set delta WT, we perform the aggregation operator, which have two inputs. One is the connected updates, and the other part is client attributes, which is non-sensitive and could be useful for aggregation. After the aggregation is complete, the server optimizer will be applied and to get the new weight WT plus 1. So in this work, we'll mainly focus on the update aggregator part. A few examples. So in Federated, the aggregator is actually a weighted average, and the Z part is actually the number of local samples. FedNova is an extension of that. Basically, it changes aggregator to include an extra local, the client attribute tau k, which is the number of local gradient descent steps performed on client k. Instead of changing the aggregator, there's also work to change the server optimizer, which is fedaddum and fedaggregate. They adapt the adaptive optimization method in centralized training, like aggregate and addum, into the federated version. So in this work, we mainly focus on the aggregation part. Basically, there are a few motivations of this work. We would like to learn to aggregate the local model updates instead of define a heuristic rule to do that. The first motivation is the weighting of the client updates and client heterogeneity. So different clients may have different hardwares or data distributions. So in the training process, we would like to assign different weights to different clients in aggregate their updates. Another motivation is the serving learning rates. So we would like to learn to adjust the server learning rate during the whole training process. Another motivation for this is to have a parameter aggregation. As I mentioned, a CTR model often have different components. So most likely, different components will have the different optimal parameter aggregation strategies. So this motivates our work to have a learnable aggregation model defined in this way. Compared to the previously mentioned aggregator, we introduced the meta parameter theta. So here, with the theta have two parts. One is theta s, which is for the adjustment of the learning rate. Another part of the theta is theta alpha, which is defined in the models to compute the weight for each client. So given the client attribute z and the meta parameter theta alpha, the function f alpha will compute the weight of the client. So after the weight of the client is computed, it will be put over a softmax to make it summing up to 1 and then do the aggregation. And here we also introduce a partition of weight indices. One typical example is by different component, so that different components will have its own meta parameter and aggregation strategy. After we have this framework, we will have a loss function to optimize. So basically, we do our meta learning in a delayed way. So to evaluate the theta t minus 1, we can only evaluate at the iteration of t. So after we do the aggregation with round t minus 1, and we compute the loss at round t, and then we can back propagate the gradient back to the server. And at the server side, we can do the gradient computation by the chain rule. So in the whole process, we do not need extra communication round or extra set of clients or data sets. We can just do this in an online setting. Now it's our experimental setting. So in all the experiment, we fix our model to be DCN V2, and we choose the server optimizer to be fat aggregate. And compared to the baseline method, which is fat average and fat aggregate, our model has better performance in both the convergence speed and also in final result. A next set of experiments, we try different types of client attributes. So we try the number of samples, so like fat average, and also the local loss, so and also the gradient norm, and also we tried the positive example ratio, like all these to compute the weight of the client. So in this table, we find that the Z2 actually the local loss values have good performance, like with compared to other method. So in all of our experiment, we choose the local loss values as the client attributes. So this is actually the distribution of the different attributes. We also do experiment on different number of clients selected for each round. So we try different portions like 1%, 5%, and 10%. And our model shows good performance in each different ratios of the clients. In our ablation study, we try like the effect of our two components, client weighting and server learning rate. So basically, each of the components has some contributions, where like the combination of these two methods has the best performance. And in the next experiment, we do an analysis on robustness of the meta-learning rate. So we try different meta-learning rates, and we found that in a reasonable range, our model is generally robust to the selection of meta-learning rate. In conclusion, for federated CTR prediction, we propose a method to learn to aggregate local model updates, which is aware of client heterogeneity and adaptive in the training process and also parameter-wise. It outperforms the state-of-art algorithms in the public benchmarks. Thank you.